Hi, good morning. Today we are going to see about differential pulse code modulation. Differential pulse code modulation is a technique of analog to digital signal conversion. This technique samples the analog signal and then quantizes the difference between the sampled value and its predicted value, then encodes the signal to form a digital value. Before going to discuss differential pulse code modulation, we have to know the demerits of pulse code modulation. The samples of a signal are highly correlated with each other. The signal's value from the present sample to the next sample does not differ by a large amount. The adjacent samples of the signal carry the same information with a small difference. When these samples are encoded by the standard PCM system, the resulting encoded signal contains some redundant information bits. The figure shows a continuing time signal x of t denoted by a dotted line. This signal is sampled by flat top sampling at intervals ts, 2ts up to nts. The sampling frequency is selected to be higher than the Nyquist rate. These samples are encoded by using 3-bit PCM. The samples are quantized to the nearest digital level as shown by small circle in the above figure. The encoded binary value of each sample is written on the top of the samples. Just observe the above figure samples taken at 4ts, 5ts and 6ts are encoded to the same value of 110. This information can be carried only by one sample value, but 3 samples are carrying the same information means redundant. Now let's consider the samples at 9ts and 10ts. The difference between these samples only due to the last bit and the first 2 bits are redundant, since they do not change. So in order to make the process this redundant information and to have a better output, it is an intelligent decision to take a predicted sampled value assumed from its previous output and summarize them with the quantized values. Such a process is called differential pulse code technique. The principle of differential pulse code modulation is if the redundancy is reduced, then the overall bit rate will decrease and the number of bits required to transmit one sample will also reduce. This type of digital pulse modulation technique is called differential pulse code modulation. The DPCM works on the principle of prediction. The value of the present sample is predicted from the previous samples. The prediction may not be exact, but it is very close to the actual sample value. The transmitter portion of the DPCM is given in this figure. The transmitter consists of a comparator, quantizer, prediction filter and an encoder. The sampled signal is denoted by x of nts and the predicted signal is indicated by x cap of nts. The comparator finds out the difference between the actual sample value and the predicted value. This is called signal error and is denoted as E of nts. Here the predicted value x cap of nts is produced by using a prediction filter. The quantizer output EQ of nts and the previous prediction is added and given as input to the prediction filter. This signal is denoted by xq of nts. This makes the prediction closer to the actual sampled signal. The quantized error signal EQ of nts is very small and can be encoded by using a small number of bits. Thus the number of bits per sample is reduced in DPCM. The quantizer output equation is given in the equation number 2. Here Q of nts is quantization error. From the above block diagram, the predicted filter input xq of nts is obtained by sum of x cap of nts and the quantizer output EQ of nts. By substituting the value of EQ of nts from the equation 2 in equation 3, we get the equation 4. From these equations, the equation 1 can be written as E of nts plus x cap of nts equal to x of nts. From the above equations 4 and 5, we get xq of nts equal to x of nts plus x of nts. Therefore, the quantized version of xq of nts is the sum of original sampled value and the quantized error q of nts. The quantized error can be positive or negative. So the output of the prediction filter does not depend on its characteristics. The differential pulse code modulation receiver is shown in this figure. In order to reconstruct the received digital signal, the DPCM receiver consists of a decoder and a prediction filter. In the absenteeism of noise, the encoder receiver input will be the same as the encoder transmitter output. As we discussed above, the predictor undertakes a value based on the previous outputs. The input given to the decoder is processed and that output is summed up with the output of the predictor to obtain better output. That means here first of all the decoder will reconstruct the quantized form of the original signal. Therefore, the signal at the receiver differs from the actual signal by quantization error, which is introduced permanently in the reconstructed signal. Applications of the DPCM are the DPCM technique mainly used in speech, image and audio signal compression. The DPCM conducted on signal with the correlation between successive samples leads to good comparison ratio. In images, there is a correlation between the neighboring pixel. In video signal, the correlation is between the same pixel in consecutive frames and inside the frames. This method is also suitable for real-time applications. To understand the efficiency of this method of medical compression and real-time application of medical imaging, such as telemedicine and online diagnosis. Therefore, it can be efficient for lossless compression and implementation for lossless or near lossless medical image compression. The advantages of DPCM are bandwidth requirement of DPCM is less compared to PCM. Quantization error is reduced because of prediction filter. Number of bits used to represent one sample value are also reduced compared to PCM. The main drawback are slow power distortion and granular noise. If there is a loss of synchronization between the transmitter and receiver, DPCM may experience error propagation. So these are the assessment questions based on the DPCM. Thank you.